Okay, let's talk about quantum numbers. So what quantum numbers are is they are a set of numbers, which actually aren't numbers at all. They're really letters. And what they do is they tell us one of the four properties of an orbital of an electron. So it's kind of like finding where this electron is. The most kind of reduced explanation I can think of is it's like the address of an electron. So if you think of your mailing address has pieces of information that go from least specific to most specific. So for example, we'll talk about, let me just tell you what the quantum numbers are first, and then I'll get back to my address example. So the first quantum number is n. So again, not a number, it's a letter. It's n, it's lowercase n. This is called the principal. This is the principal quantum number. The next quantum number is L, and it's usually drawn as this kind of cursive lowercase l. This is the angular momentum quantum number. The next quantum number is m sub l, so it's lowercase m and then a subscript cursive L. This is called the magnetic quantum number. And then the last one is m sub s. So lowercase m and then an s subscript. This is called the spin quantum number. Okay, so the principal quantum number is the first, and then it goes down n, l, m sub s. So let me just give you my home address example. So let's say somebody's home address is 1234 State Street, Bellingham, Washington. That is their address. So there's four pieces of information here. There's the state, there's the city, street, and then the house number. Each of these pieces of information are a little more specific. The Washington, this is the least specific. This would be like the N. And then the next most specific would be L. That would be like the city. And then the next is the magnetic, M sub L. And then the least specific, more specific, most specific would be the spin quantum number. So just like every house has its own address, every house can only have one address. No two houses can have the same address. Every electron has its own four quantum numbers. So, and it is the best prediction of where that electron is found. What energy level is it found in, and what type of orbital is it found in, and what direction is it spinning. That's what we're going to learn more about with these quantum numbers. This is obviously much more complicated than my little street address analogy, but it is similar. This is the least specific information about where you're located. If I said I lived in Washington, there would be lots of houses I could live in. But if I say I live in Bellingham, then there's less houses. If I say I live on State Street in Bellingham, then there's even less available. And then if I say my street address, my house number, that is specific to that one house. So every electron has its own 4 quantum numbers, just like every house has its own 4-part address. So that's kind of the least confusing way I can explain what quantum numbers are. This is kind of the basis of what you need to understand for this class. If you go on to take quantum physics or other more advanced classes, you will talk about this more. This is kind of what you need to know for this. So let's talk more about the quantum numbers, what they are. So I didn't really leave us much room, but I'm just going to go through each of these. So N, the principal quantum number. So what the principal quantum number is it's a positive integer. So like 1, 2, 3, 4, can't be 0. It describes the size and the energy of an atomic orbital. So remember back from our example, when we were seeing how much energy was emitted from an electron that's changing energy levels, n equals 3, that would have been the quantum number when the electron was here. N equals 6, that would be the quantum number when it was here. So n equals 6, these are the positive whole number integers. Those are examples. So each shell here, each of these concentric circles would represent an energy level. So this would be n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6. So it's the size and the energy of the atomic orbital. So I'm going to go through examples based on any arbitrary value. So let's just say the electron that we are dealing with, n equals 3. And we'll build on that from here. So the next quantum number, L, the angular momentum quantum number, it can be any integer from 0 to n minus 1. So what does that mean? That means if n equals 3, then L can equal 0, 1, 2. It can be any integer from 0 to n minus 1. Because n is 3, I just picked this. We'll do this for other examples. If you have an electron that is in the 3rd energy level, n equals 3, that means that it has 3 options for L. If n is 3, L can be 2. If n is 3, L can be 1. If n is 3, L can be 0. So that's the angular momentum quantum number. Let's look at this, and what L tells us is the shape of the orbital. There are some pictures in your textbook about different shapes of orbitals. I am not going to ask you specific questions about different shapes of orbitals in this class. Okay, M sub L is the magnetic quantum number. So what M sub L tells us is the orbital orientation. M sub L can be any number negative L to positive L. So N is 3. L can be anything 0 to N minus 1. So each of these limits what the next one can be. So if N is 3, L can only be 0, 1, or 2. So because N is 3, and these are my options for L, that means M sub L can be 2, 1, 0, -1, or -2. So the previous quantum number limits what the next quantum number can be. Okay, that was M sub L. I'm going to squeeze M sub S in down here at the bottom. M sub S is the spin quantum number. And it tells us the direction that the electron is spinning, either clockwise or counterclockwise. M sub S is not dependent on the other 3 quantum numbers. M sub S is always +1/2 or -1/2. So it always shows the direction the electron is spinning. So this shows the energy level that it's in. This is the shape of the orbital. This is the orientation of the orbital. And this is the direction that the electron is spinning. So you see there's lots of options now. So you could have an electron that has N equals 3, L equals 0, M sub L equals 2, M sub S equals +1/2. So that would be one option of an address for this electron. Or you could say N equals 3, L equals 0, M sub L equals 2, M sub S equals -1/2. So everything, you just can't have 4 of the exact same quantum numbers. At least one quantum number has to be different. Okay. So that's called the Pauli exclusion principle. The Pauli exclusion principle says that no 2 electrons in an atom can have the same 4 quantum numbers. So this is kind of like what I was saying before. Just like no 2 houses can have the exact same mailing address, no 2 electrons can have the same 4 quantum numbers. Okay, I am going to make another video with some examples of this, and then we'll move on.